Welcome to this explainer. Look, today you're going to want to think of me as your personal data structures and algorithms coach. We're going to completely transform your mindset. We're ditching that brute force coding habit and deploying strict ex-Google interviewer logic. Our mission here isn't just to give you a textbook lecture on string theory. No way. Our goal is to actually train your brain so that the second you look at a string problem, you automatically spot the hidden pattern, immediately know the optimal approach, and write out that code with absolute confidence. So let's dive right into it. Why do people bomb these questions? The real reason candidates fail technical screens almost never has to do with a lack of actual coding skills. Seriously, it's a failure to instantly recognize the hidden patterns within the problem. Interviewers don't hand you a problem cleanly tagged with its solution. They just give you a paragraph of English text. And if you can't extract the specific signal phrases from that paragraph within the very first 60 seconds, you're going to end up exploring brute force approaches that lead absolutely nowhere. Well, we're going to fix that today. All right, Section 1, the anatomy of strings. Before we can even think about building advanced patterns, we have to expose a massive, fundamental trap. This trap literally destroys time complexity scores in the very first minute of an interview. In most programming languages, you see strings are immutable. This means if you change a string even slightly while inside a loop, you aren't actually modifying the original string. Nope, you're forcing the system to create an entirely new string on every single iteration. So if you concatenate strings in a loop, you just turned a lightning-fast O of n operation into a catastrophic O of n squared time complexity. The secret fix? Just build a list or an array of characters as you go and join them all together at the very end. That keeps your algorithm blazing fast at O of n. Now, to think like an expert, you need to visualize strings exactly how your computer's RAM stores them. Imagine a row of houses, all perfectly lined up next to each other. Strings are contiguous sequences of characters mapped out by binary, ASCII, or Unicode codes. And because they are contiguous, you can access any character instantly in O of 1 time using zero-based indexing. You don't have to go searching door to door for the fifth character, you just jump straight to index 4. Moving right along to Section 2, substrings versus subsequences. Okay, listen up, because mixing up these two very similar terms is a guaranteed way to write completely wrong algorithms. Let's definitively settle this right now. A substring requires continuous, unbroken characters. It's like slicing a piece of cake. If your string is A, B, C, D, E, F, a substring is A, B, C. You literally slice a contiguous chunk right out of it. A subsequence, on the other hand, maintains the original left-to-right order, but it allows you to skip characters in between. It's more like picking specific M&Ms out of a trail mix. So, ACE is a perfectly valid subsequence, but it's absolutely not a subsequence. Knowing this exact distinction dictates whether you're going to use a sliding window or dynamic programming later on. Understanding sequence order becomes absolutely critical when we talk about palindromes, words that read the exact same forwards and backwards, like the word race car. This is, without a doubt, the most frequent test of your basic string manipulation skills. A super common beginner mistake here is to create a brand new reversed copy of the string to check it. Sure, it works, but it costs you O of n extra space. We can definitely do better than that. Which brings us perfectly to Section 3, pattern, 2 pointers. To avoid that O of n space trap we just talked about, we deploy our first major pattern. When an interviewer asks you to check pairs, manipulate sorted arrays, modify a string in place, or verify palindromes, your brain needs to automatically trigger the 2 pointers approach. You don't need extra arrays, you don't need fancy hash maps, you literally just need to track 2 positions at the same time. Here is the exact mechanical execution for validating a palindrome. You start a left pointer at the very beginning of the string and a right pointer at the very end. Then you step them inward, skipping over any non-alphanumeric junk characters like spaces or commas. Next, you just compare the lowercase versions of the characters at those pointers. If they match, you converge inward again. Boom. You've just solved the problem cleanly in O of n time with O of 1 space, and you never had to make a messy reversed copy of the string. Let's tackle Section 4, pattern, sliding window. Moving on to our next essential pattern. The absolute split second you read the phrases longest substring, shortest continuous subarray, or contiguous range, you must instantly default to the sliding window pattern. Instead of writing out a nested loop to check every single possible substring, which, let's be honest, would take an eternity to run, we use a virtual window that simply glides across our data. So the absolutely crucial takeaway here is this mantra. Expand right, check validity, shrink left. You eagerly expand the right pointer to pull new characters into your window. Now, if the window suddenly breaks the rules of the problem, like say capturing a duplicate character, you just shrink the left pointer until the window is valid again. And here's the absolute genius part of this. Even though it looks like there's a while loop nested inside a for loop, it is strictly O of n time. Why? Because each pointer only ever moves forward at most n times across the entire run. It's like a caterpillar crawling forward. Knowing exactly when to lock your window size versus letting it grow and shrink dynamically is honestly what separates a strong hire from a quick rejection. If the problem gives you a highly specific length, like a subarray of exactly size K, use a fixed window. You just slide it along by dropping the leftmost element and grabbing the rightmost. But if they ask for the longest or shortest valid sequence, your window has to dynamically stretch and compress as it moves. Time to level up. Section 5, Advanced, Tries and Hashing. Once you've completely mastered linear traversal with coiners and windows, it's time to talk about high-speed lookups using a trie, also known as a prefix tree. Notice how words that share a common prefix follow the exact same path down the tree's branches. The root branches out cleanly, which drastically reduces redundant memory and lets us search for prefixes without having to scan every single word in our database. It's incredibly efficient. By branching character by character like this, things like autocomplete features and dictionary checks become lightning fast. Finding a word is simply an O of M operation, where M is literally just the length of the word you're looking for. It is entirely independent of how many millions of words might actually exist in the entire dictionary. Furthermore, for heavy-duty pattern matching, we can leverage string hashing. This is such a clever technique. It lets us convert entire complex substrings into unique numerical hash values. So instead of doing a painfully slow O of n character by character comparison, we just compare two numbers in O of 1 time. This is the ultimate secret to avoiding that O of n squared brute force string matching, letting you solve complex substring search problems with ease. Let's pull it all together. Section 6, the interview decision tree. This right here is where we tie everything into an automatic rapid-fire framework. I want you to take a mental snapshot of this decision tree. Mapping the interviewer's exact phrasing directly to the right data structure in the first 60 seconds is the ultimate cheat code to passing technical screens. If you hear contiguous range, boom, sliding window. Hear sorted pair, 2 pointers. Hear prefix search, try. Hear frequency, hash map. State the pattern out loud to the interviewer immediately. It proves to them you're reasoning systematically, not just throwing darts in the dark. But look, you've got to beware. Even if you pick the exact right pattern, you must actively avoid these fatal coding errors. We're talking off by 1 index out of bound mistakes, invalid window shrinking where you totally forget to update your left pointer, confusing continuous substrings with skippable subsequences, and of course that dreaded immutability string concatenation trap we discussed right at the start. Keep your guard up against these and your code is going to be flawless. Your brain is now officially trained to spot these triggers the second they appear. You understand the core anatomy, you know the linear patterns, and you now possess the mental models of a top-tier algorithmic problem solver. This leaves you with just one final question. Are you ready to code like a true algorithmic master? Keep practicing these patterns, and I promise you're going to absolutely crush your next technical screen. Thanks for joining me on this explainer.